Thus we have seen that uniform convergence is not enough for this kind of arguments. Okay, so there is another type of continuity for a sequence of functions or a collection of functions, that is equicontinuity. Equicontinuity of the sequence of functions will give some solutions for this. Okay, so what is a equicontinuous family of? So we have defined continuity, uniform continuity of functions. Okay, so continuity means at some point x in the domain, and uniform continuity is for a collection of points or a set of points. Okay, so continuity at some x means we have for every epsilon positive there is some delta such that whenever for every epsilon positive there is a delta such that whenever dxy is less than delta, then d of f of x, f of y is less than epsilon. Okay, so this delta depends on this epsilon chosen and x. So these two things determine the delta. Okay, for uniform continuity what we have, this is for functions, this is for a collection of points or a set of points. Okay, this is at a single point, and uniform continuity is for a set of points or on the domain, for the domain itself. Okay, where we have for every epsilon positive there exists a delta positive such that the x y less than delta implies the f of x, f of y less than epsilon for all x y satisfying dxy less than delta. Okay, these points are not fixed, so such that dxy less than delta implies this, and this delta depends only on this epsilon. Okay, not the point. So whenever we have 2 points x and y satisfying this distance less than delta, then their images satisfy the distance less than epsilon. Okay, this is uniform. What may be equicontinuity? This is for a collection of functions. We have, suppose we have a collection of functions, we can name the collection, say for example script f, defined on functions defined on some set E, defined on E, which is a subset of some metric space, because we need some metric there. And here we consider complex or real valued functions only. In this beginning of the chapter we have explained it. So anyway, equicontinuity is this. So here we consider only complex valued functions. Complex means it can be real valued. So what may be the definition? You can think about it. Equicontinuity. So everywhere it is right. That means this is true for, that is given an epsilon positive, we can find a delta positive such that d of xy, whenever dxy less than delta, then d of, here it is complex value, is that the distance we consider is the usual value, Euclidean f of x, f of y is less than epsilon. This is true for any xy satisfying this condition, and this is true for every x, every function f in this range. Okay, so this is only for a single function. This is also for a single function at a single point. This is a single function at a collection of points or a set of points, and this is meant for a collection of functions. Okay, so this is the So this delta again depends only on epsilon, and this must be true. We have to get a common delta for each xy satisfying this condition and for each function. Here we have to get a common delta for all xy satisfying this condition, but for a single function. But here we need to get the common delta for every function. Okay, so this is much more stronger. Okay, so continuity, uniform continuity, and equicontinuity. And the previous questions, we have discussed some previous questions regarding convergence of sequences of functions, whether it has convergence of sequences, like that. So for such questions, this equicontinuity has to do something. Okay, we will discuss it now. The first result in this regard is suppose we have a compact set as the domain. Let K be a compact vector space. Fn is a sequence of functions in C of K. What is C of K? The set of all continuous bounded functions on K. Okay, defined on K. Continuous bounded functions defined on K. So we have a sequence of functions in C of K such that Fn, the sequence Fn converges uniformly on K. Then this sequence, this is a collection of functions. This sequence is equicontinuous on K. This is the first result in this regard. Okay, the uniform convergent sequence of continuous bounded functions on a compact set. They are equicontinuous. Okay, so that is the first result. The proof is very simple. We just analyze what are the things given. So given Fn is a sequence of functions which converges uniformly on K. Fn's are elements of C of K, means they are continuous. Okay, so we can take Fn belongs to Ck. This is the first fact given. So this is the fact given. So let us analyze what are the given things and what we can take from that given hypothesis. So given Fn belongs to C of K for okay. So that means Fn are continuous on K. Now K is a compact set. K is compact. So what we have is every continuous function on a compact set is uniformly continuous. So we have every Fn is uniformly continuous. So this is one fact we can extract from the given. Now another thing given is this sequence converges uniformly only. Second fact is this. So this is here also we can do some more things. Fn is uniformly continuous means uniform continuity means for every epsilon positive there existed delta positive such that d modulus of Fn of uniform continuity, modulus of Fnx minus Fny, we are using the definition of uniform continuity, and we made less than epsilon for xy in K with dxy. Whenever 2 points are at a distance less than delta in K, their images are at a distance less than epsilon. This is the uniform continuity. So this we can name as 1. Okay, statement. Now what is the second fact given? Fn converges uniformly. Okay, this is one given fact. The second thing is this: Fn converges uniformly on K. And from this we can say for every epsilon, uniform convergence can be used, the definition may be used, or we have a criterion, the Cauchy criterion, equivalent criterion. So we both are, okay. So in way we may have to come to the definition. For every epsilon positive, there exists an n such that modulus of Fn x minus Fn x is less than epsilon. This is true for all n m greater than or equal to n and for all x in k, because uniform convergence. For all x in k and for all epsilon positive, we can find some n satisfying this. Okay, this is the uniform convergence on K gives this norm of, what is it? Norm of Fn minus Fn less than epsilon. And from this we can conclude modulus of Fn x minus Fn x is less than epsilon for all, because norm is the supremum of all these values for all K is in. So if the supremum itself is less than epsilon, every value is less than epsilon because of that. So that's why I put it. Okay. So these are the two facts given. Now what is our aim? What we want to prove? What is to be proved? To prove Fn is equicontinuous only. Equicontinuity is proved provided. So we choose an epsilon greater than 0. For epsilon greater than 0, we have to find equicontinuity. We have to find a common delta such that for all xy in K with dxy less than delta, and for all n we must get modulus of Fn x minus Fn y equicontinuity less than epsilon. Okay. So for all epsilon greater than 0 and for all x and y in K with this property, whenever x and y in K satisfy this, we have to get this is less than epsilon provided for all n. This is the definition of it. This is the one we want to prove. Okay. And the two hypotheses can be given, or these facts can be extracted from the hypothesis. Okay, how we can